Okay, so we're on to the last little section which deals with levers. So we're just going to have a think about this. It probably makes sense to you already what a lever is, but just to make sure we all know what we're talking about. Levers are really useful because we actually use them to make sure that you lift or move really heavy objects using a relatively small force. Now you'll see if you think about trying to lift a heavy crate or something like that, you might see people with a crowbar where they kind of shimmy it under the big weight, and then they use a long pole, press down on the pole, and it lifts that big weight fairly easily. They wouldn't be able to lift it just with their bare hands. But this is all dependent on moments, and it's that force multiplied by that distance. And we're going to look at two different situations with levers. If you did GCSE DT, you would have maybe come across something like this. So you might know a little bit of the background, but if not, we're just going to deal with class 1 and class 2 levers. So in both of the two cases, you've got a load W, which is lifted by a force F using a lever of length L. And all of these calculations assume that the situation is in equilibrium. So case 1 here, the fulcrum, so remember that's that kind of pivot point like on a seesaw, is within the lever. So our lever here, our big rod, the fulcrum is actually along here somewhere. And examples of this type are maybe a seesaw, crowbars, scissors, things like that. Have a think about how they work. So if we just have a look at taking moments about the fulcrum here, this force here, if we take that force, so force times distance of F. Now this distance here, we can see the whole thing is length L, this is A, so this part here must be L minus A. Oh, I don't like doing this without a ruler, so let's just quickly grab my ruler and make that nice and neat. Now it should really go up to the fulcrum. It's a bit annoying because that fulcrum's a little triangle, but you know it goes up to that point there. So I've got my force times by my distance, so force times that L minus A distance. I should have made that a little curly L. And then my weight here is pulling down this way. This is the fulcrum, remember, this is the pivot point. So these are actually going to go in separate directions. This here, this F, is going in my anti-clockwise direction, so I'm going to take that as positive. W, I think, would pull it down this way, so it's going to take it in a clockwise direction, which would be negative. So that would be minus W times by that distance A. If you get the positive and negative the wrong way round, like those earlier examples when I showed you, it didn't really matter as long as you've got them the opposite way round, because I know it's in equilibrium because so it equals 0. So therefore I know that I can separate these two out. So I know that F times L minus A equals WA. And if I just want F by itself, the force, then that's going to be WA over L minus A. And that is something that you need to just learn and remember for some of your diagrams. I'm just doing a very wonky rectangle there, but you could highlight that when you get your notes. And if you wanted to add in here a little note about the F is anti-clockwise, therefore positive, and W is clockwise, therefore negative. Okay, so that's our first lever. If we then go to our next one, just move that one out of the way. So this is a class 2 lever. And so you can see here that the fulcrum is at the end of the lever, and you've got the weight, or the object here, kind of to the left of that. So you've got the uniform rod here, the fulcrum is at one end. Examples of this are things like wheelbarrows, if you think you tilt at one end, nutcrackers, if you've ever seen those, you've got the pivot point right at the end of it, or bottle openers. So again, we're going to take moments about the fulcrum. So it makes it a little bit easier here because we know that actually the moment through r is going to be 0 because we're going to do r times the distance, which is 0. If we have w there, this would be pulling it this way again. We're not quite sure really necessarily. It should be, so we could, I'm just going to change that actually and make that minus. What am I talking about? I need to do it the other way, don't I? This direction here is anti-clockwise, so it is positive. So I can't get my head around the clockwise and anti-clockwise at the moment. So WA, and then this one is going clockwise, so that is going to be negative. So minus F times by that whole distance L, and I know that that is 0. So if I just simplify this down, I've got WA minus FL equals 0. So again, if I want to simplify that for F, take the FL over to one side and divide by the L, so I'd have F equals WA over L. So I'm going to be crazy, do this without a ruler, say that's one formula that you need to know. Now we're going to have a look at how we might apply these, or a little bit, but we're going to just do the same kind of situation, but this time with a combined resultant force. So final example, example 3, slightly different, ends up with a non-numerical answer, but shows how you maybe combine forces. So here we have got two forces, P and Q, and we want to try and describe what the single force equivalent would be to P and Q, and say what its magnitude and line of action would be. So it's almost saying, if you combine them, how do they act as a single force? So if we do first of all the resultant, same kind of process as we did before. So we say, right, let's look at the resultant. They're both acting in the same direction, so it would be P plus Q. Again, let's take moments. And we're going to do this about this point O. So it's going to be, again, check the direction, anti-clockwise. So it's P times A, and then it's Q, and then this total distance here is A plus B. So if we replace this with a single force, and the single force would be P plus Q. Now, if we have a think about it, we've got the same line, so I'm just going to draw this in. So if we start with 0 here, and we have our little kind of dotted line, we would say have P and Q. It's going to be somewhere in the middle. I don't know what the distance will be, but my combined force here would be P plus Q. This is the distance. I'm not sure what this distance is yet. It's going to be somewhere in the middle, so let's call that X. Now I know then that if I take this moment, that's going to be P plus Q times X, and it's got to be the same as the initial situation. So that's got to be the same as PA plus Q times A plus B. And going back to the question, we wanted the magnitude of the force and the line of action. So I can find out what X is. I found the magnitude would be P plus Q. X is going to be equal to PA plus Q, A plus B, all over P plus Q. So what I can say then is that my combined force is P plus Q, its line of action is this distance from O. And then if we apply the same sort of process to the final part of example 3, part 2, so can you spot the difference? If you have a look, you've got P and Q acting in opposite directions for this one. So again, same process. Let's start with the resultant. So that's P minus Q. And then my total moment, this is where I've got to be a little bit careful, and you've got to check my directions here. So I'm going from O, so P, yes, check, anti-clockwise, so that's going to be P times A. Now Q, opposite direction, this is clockwise, so this time it's minus Q times the total distance, which I know is A plus B. Again, if I think of the same principle, so this time I'm going to draw this diagram underneath. That might help us a little bit just to get our heads around it. So I'm going to apply the same force. Now, I don't know what direction it is. I don't know the the magnitude of each of these forces. So I'm going to guess and say, well, will it be somewhere in the middle? Perhaps not directly in the middle, but in between, perhaps I should say, rather than middle. And this time it's going to be P minus Q. I'm kind of assuming that P is bigger than Q. If I make that assumption, that my final answer will tell me, won't it, when I solve this numerically, if it comes out as negative, I know that it's the other way. So I replace with a single force. And this time the magnitude is P minus Q. And so again, if I equate the moments this time, I'm going to say that's distance x like I did in the last one. So therefore, I know that P minus Q times that distance x, put the little arrows in, is equal to the total moment from before, which is PA minus Q times A plus B. I don't know why I've done that line, I'm preempting it, aren't I? So let's go to the next line, which is PA minus QA plus B all over P minus Q. So I know that the magnitude is P minus Q and the line of action is that distance away from the point O. Okay, so hopefully that's helped a little bit with some of the explanations. If you now have a go at exercise 10.1 on page 226 and just let me know if you have any problems with it. I hope that it's helped a little bit having this brought to life. Sorry about the little bits and bobs and mistakes I've made along the way. It's a little bit weird doing this by myself, but it's very lovely thinking that it might make it a little bit more interactive for you. Okay, take care, bye bye.